Great. Well, thank you very much for the introduction. I'm Ben Jones, and today I'd like to talk to you about cases where users are unable to access the legitimate DNS route. So this is a joint work with Nick Feamster, Vern Paxson, Nick Weaver, and Mark Allman. To begin, I think we would all agree that DNS is critical infrastructure. We'd all agree that the internet needs some form of human understandable addressing, so the internet needs DNS. And the DNS route is a critical piece of this infrastructure. The DNS can't operate without the DNS route. But what would happen if users were unable to talk to the real DNS route? And it turns out that this would have pretty major implications, both for security as well as internet governance. But before I dive into that, let's talk about what the DNS route actually is. So the DNS route is the top of the DNS resolution hierarchy. So what this means is that, for example, if you try to resolve google.com, you start by getting the name servers for com, and then you get the name servers for google.com, and so on. And so what this means is that every time you resolve a domain name, you either talk to the DNS route directly, or you use a cached response from the DNS route. So the DNS route consists of 13 logical servers, and each of them is assigned a letter, A through M. And that's how we refer to the routes. And these servers are anycasted to varying degrees. So LRoot is the most anycast, which I checked earlier this week, and it has roughly 144 instances around the world. And BRoot is the only unicast route, so it has a single instance in California. And these servers are located all around the world. So for example, if you look at this graphic here, it displays the distribution of anycast instances for the DNS route all over the world. And if we look at Europe, we'll see there's two little bubbles, 52 and 90. And those bubbles correspond to aggregations from the surrounding area. So that means that there's 142 root instances in that area of Europe. So clearly there are a lot of these servers, and they're pretty broadly distributed. So would we really care if someone were to be talking to an unauthorized route? Would we really care if another one of these servers were to pop up? And it turns out that we actually would care, because in some cases DNSSEC is not going to be enough for us. DNSSEC provides integrity, but it doesn't provide availability. So what this means is that DNSSEC guarantees that if I get a response, I can tell you whether or not it's correct, but it's not going to guarantee that I'm going to get the correct response. And this is important because censorship is an attack on availability. We know that many countries already care about censoring access to the internet, and many of them already do this with DNS. So censorship is a very important attack to consider. And if an attacker has control over the DNS route, then they can censor any domain that they choose. Furthermore, masquerading DNS routes affect internet governance. And this is really important, because if countries can create their own version of DNS, they can choose to create their own names. They can choose to have a completely separate internet from the rest of the world. So for example, Iran has talked numerous times about creating a halal internet, a completely separate internet from the rest of the world. And this is not something we really want. We tend to like to think that we'd like to be able to talk to every other host on the internet. So now that we've justified that we really do care about finding out if users can talk to the real route, what is it that we're actually looking for? So in this graphic, all the way on the left, I have some host who's interested in talking to the real DNS route. And all the way on the right, I have the actual DNS route. And there's two types of manipulation that we're concerned with in this study. So the first type is a DNS proxy. And in case of a DNS proxy, we're talking about a sort of application level attack. So what we assume with a DNS proxy is that it's going to be intercepting only DNS traffic that would otherwise go to one of the DNS routes. So for example, a ping to the real DNS route would go through, but a DNS request would be stopped. In contrast, we're also going to be looking for DNS route mirrors. And in this case, we're treating this as more of a network level attack, where all of the traffic that would be destined towards that root server's address will now be going towards the root mirror instead of the actual DNS route. And these sort of manipulations could be happening either within an ISP or at the level of a national internet above multiple ISPs. So to define this problem, what we're trying to find out is, can users talk to the real DNS route? And our solution to answer this problem is to collect data from a large set of users, and then to look for anomalous response times and anomalous server identities. We're checking if our data matches our expectations about the DNS route. And we're also going to focus on BRoot, because there's only one instance of BRoot, which substantially simplifies many of our analyses. So from here, I'm going to start with a discussion of my data set and methods before diving into the results of what we found. So we used two measurements for this study. So the first set of measurements were from end users, specifically the RIPE Atlas platform. And the second set of measurements were from the internet's core, looking at BGP updates and RIBs. So from RIPE Atlas, there are a number of measurements that are automatically conducted from every probe to the DNS route, which was quite useful to us when we were looking to understand DNS route manipulation. So the first data set we looked at was pings from each of these probes to the DNS route. And RIPE Atlas conducts a ping, in this case to B route, every 4 minutes. So we had several thousand ping measurements over the course of a week of data. And we use this to look for proxies and route mirrors. We also looked at HOSTNAME.BIND queries from RIPE Atlas probes. And a HOSTNAME.BIND query is a special DNS query that asks the DNS server that you're talking to identify itself. But I'll talk more about that in a minute. We did a one-off study of these to try and find proxies and route mirrors. And we also looked at trace routes. So the trace routes from RIPE Atlas are conducted to the DNS routes roughly every 30 minutes. But we just looked at a one-off sample of these trace routes to try and find route mirrors. And our ping and hostname.bind queries came from around 6,000 RIPE Atlas nodes, whereas our trace routes came from around 2,000 RIPE Atlas nodes. Looking at BGP, we looked at RIPE RIS from roughly a week of data, looking at both RIBs and updates to try and find route mirrors. And we looked at route views data, just the RIBs, to also look for route mirrors. Alrighty. So using this data, we then tried to find DNS proxies and DNS route mirrors using two methods, as I mentioned before. So we're going to look at response times to see if the response beat the speed of light using RIPE Atlas pings. And we're also going to look at the server's identity. So is the user talking to the real DNS route? And we're going to use RIPE Atlas hostname.bind queries, trace routes, and BGP data to try to better understand if the server that the user is talking to is the legitimate DNS route. Starting with response time, our question is, did the response beat the speed of light? And in order to answer this question, we started by geolocating our probes using RIPE Atlas's built-in geolocation information, which is provided by the user, and using MaxMind's IP geolocation service to geolocate the public IP address of each probe. We then found the minimum RTT from the week of data, the week of pings we had from each probe in this data set from RIPE Atlas. And in this case, we're using the minimum RTT because we want to see if it's feasible for the probe to talk to the DNS route in a faster than it would take speed of light. And in this case, we want ideal conditions that are as free of network load and congestion as possible. So we're interested in the minimum response time. And then we compared all of the responses from within a region against the expected RTT being the speed of light, and looking for outliers from all of the response times in that region. Next, we also looked at server identity using hostname.bind queries. And just to provide a little bit more information about hostname.bind queries, this is a special DNS query that when you issue it to a DNS server, the DNS server immediately responds back to the query. So this is not recursively answered. The first DNS server that sees a hostname.bind query immediately responds. And so sending these queries, we collected the server's identity, which is the value in the hostname.bind response, as well as the response time for the hostname.bind query. And we compared these values against the expected value from broot. And then we additionally compared ping and DNS response times. So our assumption is that we would see a similar response time for pings and DNS responses if they're going to the same location, that there might be some variance, but they would be roughly equivalent. And if the DNS response time was substantially lower, then we expected that a DNS proxy might be in use. Alrighty. We also looked at server identity using traceroutes. And our hypothesis here was that route mirrors may have a different last hop or penultimate router than legitimate users. So basically, let's imagine that you create a DNS route mirror within your ISP. Then traffic from your users to your route mirror is unlikely to ever leave your ISP. So in this case, you're going to have a different last hop than all of the legitimate users talking to the real B route. And so to illustrate this on the graphic over here, we have probe A, which is talking to the legitimate B route, and we have probe B, which is talking to some route mirror. And as we can see, their penultimate routers are different. One is AS1, which is legitimate, and one is AS2, which is not. So in this case, we extracted the last hop routers from the right bat list traceroutes and then compared them. We also used traceroutes to investigate the hypothesis that an ISP might redirect multiple root server addresses to the same instance. So the idea here is that if you're manipulating the DNS route, you might choose to manipulate multiple DNS root servers. And you might try and save some administrative effort by redirecting all of these servers to the same instance. So in this case, we're evaluating this hypothesis by comparing the trace routes to two different destinations. So in this case, we see that we have a measurement probe all the way on the right-hand side of the screen. And in this case, the measurement probe is getting to B route through AS1 and is getting to L route through ASN2. So we expect that these two trace routes will be different. So you could think about in the previous example where we're taking multiple probes and comparing their paths to B route, we're sort of taking a many to one approach. And in this case, we're sort of taking a one to many approach. Excuse me, going from each probe to the two different routes. And finally, we looked at server identity using BGP. So our hypothesis here is, what if an ISP tried to use BGP to redirect users to their root mirror? So what if they used their internal BGP tables to try and redirect users to a root mirror? And what if they accidentally propagated that route? So what if the ISP was using BGP as the tool? So this might be similar to, for example, we know that in Pakistan, they used BGP to block access to YouTube. So they just basically routed all of YouTube's traffic away from Google to some address that didn't exist. So we might expect the same thing here, but to a DNS root mirror within the country. So what we were looking to see is if anyone was doing a prefix hijack on B route by accidentally propagating this advertisement. So we collected, again, ribs and updates from RIPE RIS and ribs from route views. And then we looked for unexpected announcements for B route's prefix. So now that we've discussed these methods, I'm going to dive a little bit more into our results. So first, we looked to detect DNS proxies by comparing the response times between ping and DNS measurements. So in this case, we're taking a ping measurement and subtracting the DNS response time off, and then plotting this for different countries. So in this case, the x-axis is in terms of milliseconds, and it's the difference between the two response times for several countries in Africa. And what we see is that generally, the response times are pretty similar for ping and DNS response times. So they're pretty closely clustered around 0, though we see a slight spread towards the negative. And what that means is that DNS is typically taking a little bit longer than the ping responses to arrive. So further to the left means that the DNS response is taking longer, and further to the right means that the ping response is taking longer. And what's really interesting here is if we look all the way over to the right, in Kenya, we see that there's a RIPE Atlas probe that is getting a DNS response 300 milliseconds faster than it's getting a ping. So we investigated this further, and we found that there was a DNS proxy in use. So basically, the DNS proxy was intercepting the DNS query to the DNS route, but pings were able to travel successfully to the real DNS route. And using these techniques, we were able to find a total of 10 DNS proxies. And this data was also consistent with our HOSTNAME.BIND responses. The values were inconsistent for each of the DNS proxies we found as well. So next, we attempted to detect unauthorized DNS routes. And this is going back to our response time measurements. So in this case, what we see here is a scatter plot of response times, of ping response times to two different routes for a variety of servers in Asia. So this is a subset of responses. This isn't all of the responses from Asia. And so on the y-axis, we have response times to L routes, which is heavily anycasted, and we expect somewhat lower response times for. And on the x-axis, we have response times for B route, which, remember, is only located in California. So we expect fairly high response times. And what this shows is that generally, the response times are above 100 milliseconds. but we have a single outlier, which is being pointed to, indicated by the arrow, which has a response time of less than 5 milliseconds to broot, despite the fact that it's located in China. So using this method, we were able to successfully detect that there is a DNS root mirror within CERNet in China. So in this case, it had actually a higher RTT to L root than it did to B root, which was surprising. This is the only DNS root mirror we were able to find out of the roughly 6,000 ripe atlas probes we looked at. So these, these root mirrors do appear to be very, very rare, but it is interesting that we were able to find one. And again, we're finding this by seeing a much smaller ping than we would expect from the rest of the responses in the region. And in fact, this is much faster than the speed of light. So for comparison, the speed of light in fiber is roughly 50 milliseconds to get from China to the US. In reality, we expect it to take longer because the 50 milliseconds is computed using the Great Circle distance, and we expect a more circuitous route with undersea cables. And we also expect that there's going to be some switching delay from actually dealing with the packets, which is why most of the responses are much larger than that. So interestingly, we found that detecting DNS root mirrors was actually more difficult than you would expect because we needed to differentiate between errors and legitimately low ping times. So in this case, we had one probe that incorrectly geolocated with both of our geolocation data sources. So for example, in this case, we had a probe that both MaxMind and the user who would install the ripe atlas probe said that it was in Switzerland, but a traceroute indicated that it was actually in New York. So that was an interesting finding. And then we also had two probes that incorrectly interpreted ICMP errors as ping responses. And we know that these are ICMP errors. In this case, we were able to see the TTL value, and we saw it had a TTL value of 255, so it had to be coming from the next hop, and these probes were not one hop away from B-root. So to demonstrate why this is actually quite tricky to deal with and detect, this is a graph of the ping response times from one of these probes. So at first, we were a little bit curious what was happening. We thought maybe there was some routing issue or it was switching between a route to a root mirror and the legitimate route. But we actually found out later is that all of the lower response times are due to ICMP errors, and the response times that are around 160, 175 milliseconds are the actual response times to B-root. So I guess a little bit more information about this graph. On the y-axis is the RTT in milliseconds reported by the ping, and on the x-axis is the date that this is collected. So this is looking at a week of measurements from a single ripe atlas probe, and there's a ping here every 4 minutes. So in the end, we manually explored all of the low ping times to ensure that we were reporting actual DNS routes as opposed to something else, to an ICMP error. So we found 4 potential root mirrors, and we eliminated this down to 1 actual root mirror. We reported this bug to ripe atlas. I'm sure they fixed it by now. So let's see. So in summary, we applied a number of different analyses, and we were able to find a total of 10 DNS proxies and 1 root mirror. So using, and all of these responses were consistent with each other. So we found 10 DNS proxies and 1 root mirror with anomalous HOSTNAME.BIND responses. And we found the same 10 DNS proxies, comparing our DNS and ping response times. We found 1 root mirror using our ping response times, but we found no evidence of manipulation looking at trace routes of penultimate routers. Looking at path sharing between trace routes, we saw no evidence of shared paths between routes, and we also saw no evidence of hijacks when we were doing our BGP analysis. So in conclusion, we've addressed an important research question, which is evaluating whether users can talk to the real DNS routes. We developed some new measurement techniques to try and answer this question, and analyzing data from ripe atlas, we're able to find 10 DNS proxies and 1 root mirror. So I'm happy to take questions. Feel free to email me at the address below if you'd like. So thanks.
Thank you very much. Questions? Well, while you think about it, any hope that there will be a bit more meat? Not that we want to find anything actually,
right.
Sadly, in this topic,
right.
But do you think there will be something else than China? Which would have been my question otherwise if you didn't spot it.
Right. I mean, Yeah, so it's a good question. So we tried to be overly conservative in terms of finding things. I don't think that there's any more root mirrors to be found in our data set. There might be some DNS proxies that we missed, but that seems somewhat unlikely. I don't think that in general on the internet we're going to see too many root mirrors. It seems unlikely. It seems like a lot of work for little effort. I do think that there are a lot of DNS proxies. So comparing our results with existing work, comparing with Netalyzer, for example, Netalyzer has done a study of DNS proxies, and we found about 1/10 of the number of DNS proxies they found. So I don't know if that deals with, from Ripe Atlas. So I don't know if that deals with different representation among the measurement probes from Ripe Atlas versus Netalyzer, or if we're just missing more of those DNS proxies.
One question.
So let me ask you something. Assuming that someone puts in front of his DNS proxy the device which adds extra delay on the answers, would it
Right.
be able to detect the behavior of DNS proxy?
They add extra delay. So it depends. So if it depends on if they've it would be possible in all of the measurements that we've proposed for someone who really didn't want their DNS proxy or their DNS route to be detected, their root mirror to be detected, to avoid being detected using our techniques. But that does seem unlikely. We guessed in some of these cases that the DNS proxies might be in use to improve performance. So in the example I gave about Kenya, we see a 300 millisecond faster time to get a DNS response than actually talking to broot. So in that case, it would raise the question of why are you using a DNS proxy or a DNS route if you're not seeing a performance improvement.
So in one of your plots, you were showing that DNS response are way slower than Bing.
Yeah, it wasn't.
Investigate why. I mean, is just because of the country where this is happening, or is a?
Let's see.
Do you that? Oh, yes.
Yeah.
In South Africa, you have this extreme on the left. Do you know why it's being that bad?
I don't have a good answer to that. Sorry. I don't know. I mean, maybe we estimate maybe this is something to do with control path for handling ICMP responses versus actually having to do some crunching to answer DNS responses, but I don't have a conclusive answer for you.
Any more questions? Otherwise, let's thank the speaker. Thank you.
Thanks.